So what we can do is just taking the log. So L of the theta is just taking the log, get rid of those exponential and those things, so it becomes VC transpose V omega, but we still have log. And summation over W prime, VC transpose VW. And just for any problem, we take derivative with respect to the variables that we have. So this becomes VC minus the derivative of this term with respect to V of omega becomes 1 over summation VC transposed V omega summation over W prime times e to the VC transpose V omega. And look, we've just got the probability of word given the context. And of course, times VC. So if you simplify this, it becomes VC minus probability of word given context time VC. And you simplify that by 1 minus probability of W given context. And now you're ready for your beautiful gradient descent. So VW new is equal to VW old minus, we need some coefficient, some step constant, and then your gradient. What is your gradient? We have just calculated that. So this is VC1 minus probability of word given vector, given context. So as I said, at the denominator, we have to sum over a huge data. So it's a large corpus. And so this is a gradient descent, and this is some coefficient. So in order to deal with this problem that your denominator is so big, we need something like negative sampling. So let's concentrate on the method of negative sampling. And we use it for skipgram because you could use it for continuous bag of words as well. But for simplicity, we use skipgram. So what you want to do, you want to turn an unsupervised learning. So if you understand this, that you want to convert an unsupervised problem to a supervised problem, then that's it. You know why we are doing this. So we have a context, we have a word, and we have a target because it's a supervised learning. And in our supervised learning, we have, for example, your context is orange, and your word is juice. So target is 1 because juice usually comes after orange juice. But you want something out of the human context, human text, and something. So you randomly negative sample it. You randomly sample it. So everything like, for example, this one book, and sometimes this becomes like rational things, but we don't care. We have just done it randomly, and we don't care if it becomes rational for the human speech, human text, or becomes irrational, something like a bad book, a crazy, I don't know, something that is not rational, because you're just adding two words together so these are out of the corpus. So as I said, the trick is to define two sets. D is the set of all pairs, W and C, and we make sure you can discriminate from random adversarial words out of D that are in the text. So D prime is just set of all pairs that are not in the text. And you put Z equal to 1 if W and C is in the corpus, and Z is equal to 0 if W and C is not in the corpus, so it belongs to D prime. So just to review, we say that the probability that Z becomes 1 given the word in the context is the probability that WC is in D, and the probability that Z is 0 given the word in context is the probability that W and C is in D prime. So knowing this, we can now, it's like classification problems that we use. For example, logistic regression, which want to try to model the posterior directly. So if we have a posterior like P of Z given X, we have some likelihood P of X given Z and some prior P of Z and some marginal or evidence given P of X, the marginal. And the logistic regression tries to model the posterior directly. So the probability of Z equal to 1 given word and context is equal to 1 over 1 plus e to the v C transpose V of omega. And the probability of Z equal to 0 given W and C is equal to, let's see, e to the VC transpose V omega plus 1 plus e to the VC transpose V omega. Omega is W. I sometimes say omega and sometimes say W. So forgive me, please, for this problem that I have in my unconscious neural network inside my brain. So we just add and we just multiply e to the VC transpose VW. So what happens, it becomes 1 over 1 plus e to the minus VC transpose V omega. And so the probability of Z given WC and theta becomes 1 over 1 plus e to the minus VC transpose V omega to the Z times 1 over 1 plus e to the minus VC transpose V omega. And so it is completely equivalent to matrix factorization idea, if you're familiar with. And the authors try to write it like this, very compact form. So this is the sigmoid acting on C, the W, and also minus C, W for negative samples, for multiple negative samples. So again, our theta is that we want to infer, we want to estimate, is VC and VW. And again, we use maximum likelihood method. So L of theta, your likelihood, becomes the product over all of the pairs in the corpus and outside the corpus, both of them. So this becomes 1 over 1 plus e to the VC transpose V omega and 1 plus e to the minus VC transpose V omega. This is just a compact form because if you put 0, if this becomes 1 and this becomes 1 over this. So it's a compact form of what I've told you about that. But this is the product of these things because we want to calculate the likelihood. And so the likelihood, if you take the log So the trick is so there is no trick because we just take the log and thus everything is easy. E to the VC transpose VW plus 1 minus Z log of 1 over 1 plus E to the minus VC transpose VW. And now we want to simplify that. So L of theta is just over all pairs in the corpus, and the log of 1 over 1 plus E to the VC transpose VW plus W and C in outside the corpus. So it's the log of 1 over 1 plus E to the minus VC transpose VW. So read 2014 article of Goldberg and Levy. Goldberg and Levy. So because it presents the objective for the entire corpus. But the Mikolov for negative sampling because it derives, this article derives Mikolov negative sampling word embedding. And Mikolov presented for one example only. So the difference is that Mikolov for one example, for one pair, and K examples. But the Goldberg and Levy represented for the entire corpus, D and D prime. So that's the difference between their derivations. And now we are ready to talk about scriptgram again. So we want to, for example, we have some turning into banking crisis as. So if this is the center, so this one is the probability of word T minus 1 given WT, and this is the probability of WT minus 2 given WT. This is the language, same thing as these things. So your cost function J prime theta, we want to maximize it. So it is the product over J from M to minus M, because we have a window of length 2M. So the probability of T plus J given WT and your vector representation of a word. So this theta could be the augmentation. For example, V of vector of government, vector of home, vector of freedom, vector of and then again for the U. So U of government, because each word, depending on if it is context or a center, has a different embedding. U of home, U of freedom. So the same thing here, but so U and V are just context and word, context and center. So we have two representation for any word, because it depends on whether it is context or it is the center. So the probability of your output, which is your context, given your center word. So now I call it center, not context. This is center, and this is the output, which is context. So this is E to the U output transpose VC. So we exponentiate this in order to make it positive. That's a trick. And we normalize it to give probability. So we normalize your W from 1 to V in order to give probability of UW transpose VC. and we use softmax for that. So if you take derivative with respect to VC of log of XPU output transpose of VC over W from 1 to V exponential UW transpose of VC. So let's see what happens. First of all, it is log of exponential of U output transpose VC, and log of something A over B becomes negative things, A minus B, log of A minus log of B. So this becomes log of W from 1 to V e to the UW transpose VC. So we want to evaluate these terms 1 and 2. So this becomes, so the first one is simple. It becomes UO transpose VC. And then, of course, this is itself is simply U out. And then the second term is just, so this comes inside and becomes log of W from 1 to V e to the UW transpose VC. And this is, if this is the Z from the chain rule, so recall the chain rule. For example, you want to know f of g of u. So if we call it Z, so we can use the chain rule for this. So I simplify that because it's elementary mathematics. E to the UW transpose VC that x from 1 to V e to the UX transpose VC UX. And this becomes U output minus x from 1 to V e to the UX transpose VC divided by summation over the corpus e to the UW transpose VC. And again, you notice that this is just P of X given context, and of course times UX. So this is simplified to U output, the observed one, minus X plus 1 to V. So this is like expectation vector, because the probability times that thing, so it becomes the expectation. So this is the center, this is the context word. So we use stochastic gradient descent because the corpus is big, and what is that stochastic gradient descent? You have theta of nu is theta of old minus your step constant times derivative with respect to theta of your j. And we minimize j by doing this iterative algorithm. Now I want to talk about linear Dirichlet allocation. So it is a 2003 article, very seminal, a breakthrough article by David Bly. Very creative person. I really like him. And, Andrew Ng, very popular in deep learning. And Michael Jordan, the great statistician in Berkeley, I think. Michael Jordan. So the goal is that we want to know the probability of topics. So it's topic modeling. You have lots of documents, and you want to find the topics. But the challenge of this method Even in 2022, people don't know how many topics they should use because it's a hyperparameter, and mathematically we don't know how to derive that because it's a hyperparameter. So we always have problems with hyper. It could be anything, and we cannot try an infinite amount of numbers in order to understand which one is